That's the lower quality microphone. Are you hearing me? Yeah, tell me if you are hearing me now. Okay, now it shows that you are hearing me, but I think it's okay. Like I'm saying some. Yeah, okay, it's working. Yeah, okay. Starting over one more time. Hi, good morning, everyone. This is Ali Rasek. I'm a structural engineer with HDR, and I am teaching Civil 459 at University of Victoria. Today is June 28th. This was very funny because like when you were not hearing me, what I was saying was that every session I try to use the best quality microphones and just like video recorders so that the quality of the recorded session is the best and you guys can like listen to it one more time. And it's completely funny that exactly today it was not working. So I switched from the microphone that I thought it's the better one. For some reason, it's not connected. So we are using the laptop microphone, which is slightly lower quality, but it's working. So we can continue today. Normally, I try to really think ahead and use better equipment for this class so that you hear me well, the recording quality is high. And I was also saying that today I understand if the class is slightly less populated because some students, some learners are working on the some meetup, which is the deadline is today. Now, yeah, we are in module number 6 now. We will proceed to module number 7 shortly. 6 and 7 are the core of the course. And the other important parts are really in terms of order. 6 and 7 are on top. 1 and 2 are important. 8 and 9, only brief introduction. And yeah, then 3 is somewhat geotechnical. 5 is slightly geologist, seismologist. But all of them, I mean, an introduction to each one of them is good for a practicing structural engineer. So hopefully everybody is enjoying. And so coming here, the date is 28. We should have already started number 7. Number 7 is short, but however, yeah, we are still in 6, which is the core. So I don't mind repeating it slightly longer and finish some other modules faster. Besides the fact that maybe we will have some extra time on 26 and 2nd because there are fewer teams than what I planned for. Now we can continue with the course. Clean up a little bit. We can minimize this. Hopefully no surprises. I'm still very surprised. I have a very good microphone here in terms of quality, and maybe somehow it's not connected. My toddler also sometimes plays with things, and maybe he managed to turn off the microphone for me. That's fine. Yeah, because the laptop microphone, I mean, it's good, but not excellent. So, but I'm pretty sure you guys are hearing me well. Now we are in equivalent static force procedure. This is very important. We don't mind quickly recap. I like going to a recap. We repeatedly discussed the importance of load paths and that the structural engineer should understand the load path both for vertical and lateral. We had this discussion that the code somehow emphasizes different load paths for vertical and horizontal, but then I mean, practically in engineering, sometimes they are slightly mixed. So it means I interpret it as different capacities. Don't use the same capacity that you use for vertical for lateral. That's what the way I would interpret it. Like if there is the same system, 50% of capacity is for vertical, 50% for lateral. So they don't alternate, they add up to each other. And typical lateral load resisting system through bracing. And yeah, it looks like more advanced. Maybe there's dampers in here. So in this covered area, or maybe it's like concrete, which prevents buckling. Yeah, I cannot remember where I got this from, and I didn't carry on the caption, but it's like a slightly more advanced bracing than usual. Types of seismic force assisting system, as is practiced in structural engineering, moment frames, which carry the lateral force because these connections are kind of rigid. They can transfer moment through the connections. Therefore, the naming moment frame. Brace frame, where braces are used for lateral load resistance. And they could also be mixed, like both moment resisting and bracing. Shear wall, let me check the chat. Okay. Shear wall, where we use some sort of wall system to prevent lateral force, could be concrete shear wall or wooden sheets in smaller buildings, or steel. In practice, I haven't seen a steel, but I mean, it's used. So many other people are using it, other engineers are using it. So this wall could really be a steel sheet. Seismic force assisting system. What do we mean by shear wall or shear or coupled wall or shear wall with opening? Steel plates could be used in high rises, apparently, as shear wall. And masonry shear wall definitely is used, and wood panels are definitely used. Bracing frames, mostly in steel. Concentric, meaning that they meet each other within the structure, the two braces. Eccentric, meaning that there is a eccentricity, they are away from each other, which creates a shear energy, we can call it shear energy dissipation, or energy dissipation through shear, which is a good mechanism and causes good amount of ductility. Moment resisting, where we have rigid connections, we can transfer moments, and this structure provides good ductility. Earthquake forces in shear wall systems. And the shear wall, like the usual shear wall, concrete shear wall, which could also be like some sort of a duct around the elevator, and coupled wall, where there are lots of openings, and therefore we have coupling system, meaning that there is also like transverse shear. There are like beams with lots of shear in vertical direction, besides the fact that the normal shear wall will have a lot of shear in horizontal direction. And in this system, even in the regular shear wall, the ends of the wall will be designed for huge tension and huge compression. With the case with steel plates, where those steel plates transfer a lot of shear, and they appear to be like, if you think theoretically, steel is the best product to provide ductility. So I would say this system also provides a lot of ductility. And again, in the base, we have a lot of tension on one side and a lot of compression in the other side, which we should design for. earthquake forces in braced frame systems. In braces, the lateral load is transferred mainly through bracing, causing tension and compression in the braces. And they also result in creating tension and compression in the columns. Where there is eccentricity beside the phenomena of regular bracing system, we have a major shear between these two connections, like the connections that connect braces to the beam. And this major shear force will result in a good energy dissipation system. And because this is narrow, that's another benefit, that we know where the damage is concentrated, and we can prevent or think ahead that it doesn't result in collapse. And after the earthquake, post-earthquake, we can exactly locate the location of damage and go there and fix it. Maybe if any of them is sheared out, we can basically cut it and replace it. So I think in terms of post-earthquake retrofit, this is also a good idea, besides the fact that it dissipates energy. In moment resisting frame, as I said, we have a lot of moments in beams and columns, which will result in plastic hinges. Plasticity means dissipation of energy. Now, recap of the equivalent static force procedure. In the equivalent static force procedure within the National Building Code of Canada, so the way they think about it is a triangle, meaning that like the loads reverse triangle, meaning the lateral force are increasing by elevation, plus an additional portion which is added only to the roof because it's basically accounts for higher modes, meaning that the deformation shape and the shape of the equivalent lateral force is not exactly triangular. It should be like a little bit nonlinear, and the way NBCC accounts for this nonlinearity is through adding the FT. So because the total force, we don't want to change it, we reduce FT from the total force. We distribute it with these weight functions through the height to create this triangle. And then we apply that additional portion only to the roof, which is a portion of the V, total lateral force, or what we call base shear, because the shear at the base, even looking at this picture, it should add up to V. So we have calculated the value of V, we have that equation, which gave us an estimate of base shear, means the total shear at the base. And however, for detailed design, we need to distribute it through the height, and we use this scheme to distribute it in the height. And now that we are talking about the distribution through the height, meaning higher a system with more than one primary mode, with more than one important mode, we can re-emphasize the effect of higher modes. And in a way, we increase the base shear because of the higher mode effect using the parameters from the code. But then we realize that we are overestimating the overturning force, then we reduce the overturning factor. And this reduction is applied at every level of the structure except for the top 40% of the height. So we reduce it from base to like it looks like the 3 story out of 5, that's 60%. We reduce it between these 3 stories. These 2 stories we don't reduce, we keep it higher because of the higher mode, we are more worried about the top of the structure. And we show the table, the corresponding table is table 41811 that has both factors, yeah. So MV for increasing base shear, which looks like it's mostly applicable to walls, wall frame systems. So mostly in wall frame systems, we are accounting for higher modes. In a lot of other structures, say first item, which is moment resisting a structure, appears that no matter how tall the building is or what your period is, you don't really increase it. But then for walls, wherever walls are included, for longer periods and for taller buildings, we increase the base shear because the higher mode effects are apparently important. On the other hand, the reduction factor that we are used for overturning checks looks like it's usually important for taller buildings and for higher mode of the structure. And sorry, for structures with longer period. So for longer periods, for structures with long periods and for tall buildings, we have reduction, serious amount of reduction to account for higher modes. That's the effect of higher modes. And we are allowed to reduce the overturning moment. And again, this is more pronounced for walls. So it looks like this is a little bit counterintuitive that you think that walls are rigid and therefore they are primarily acting in their first mode. But it looks like for walls, the effect of higher modes are even more important than a steel building. But yeah, they have done lots of calculation and tests and provided us with a simple to use table. Now, this solution that was provided last time, and we reviewed it this time, cannot always be used, and we need a factor which is called regularity, which we will discuss shortly. The code allows for this simplified solution only in seismic category 1 and seismic category 2. We will soon review what seismic category 1 and 2 mean. And they should meet any of the following criteria. So there's a or between them. Seismic category SC1 or SC2. So any building in these two seismic categories, because it means a smaller risk. Because we are taking a smaller risk, then we can use the simplified solution, or a structure which is regular, like for seismic category 3 and 4. A structure should be regular, less than 60 meters, and the primary period should be less than 2 seconds. Say 20-story building, about that value. And if your structure is irregular, and if you are in seismic category 3 and 4, then you come to this one, limited to certain types of irregularity. Looks like number 1 and number 7 are excluded. Besides, it's very limited in the height, like only 20 meters, and limited in the primary period. So that's what we explain further. Seismic category I don't know if it's identical to the ASC 7, but almost the same concept came in. So they also have very similar idea there, or maybe identical. I haven't checked these numbers. How to define seismic category for the building. We look at two parameters, the short period response and long period response. Short period at 0.2 second, the long period at 1 second, multiplied by the importance factor. And when we look at the short period, seismic category 1 is when this combination is less than 0.2, which means 0.2 G. And when it goes between 0.2 and 0.35, it's seismic category 2. And 3 is less than 0.75. 4 is greater than 0.75. Looking at response at long period, numbers are different. Less than 0.1 is category 1, less than 0.2 is 2, and less than 0.3 is 3. And then greater than 0.3 is seismic category 4. So we do, in a way, determination of the category twice, once using this column, once using this column. And the worst of the two is seismic category of the structure. Worse means larger number. So the larger the seismic category means that we are having larger risk. So the seismic category, we are discussing seismic categories. So if you are between these two seismic categories, do use the simplified method with no limitations. If you are in these two seismic category, higher risk, seismic category 3 and 4 with larger accelerations, then there are limitations. Like we should then figure out if our structure is regular or not regular, and for each one of them, there are certain limitations. Now let's figure out the regularity. So by regularity, we mean that the structure doesn't change in plan and in elevation. And the changes that are important to us are stiffness and also strength and the weight and the geometry, the shape, and the torsional effect. Like the structure might appear to have uniform geometry, but because of certain design, maybe the center of gravity and center of mass are not located at the same location. So that is a torsion that will cause torsion and will cause a structure to be considered irregular. And the presence of these irregularities result in height limits. And if we don't meet the height limits, if the code prohibits using simplified static, then we have no way but to use the dynamic analysis. But the good news is that you already know how to use dynamic analysis, so you can proceed with your SAP 2000 or similar program. An extensive, sorry, this is moved too fast. Is this? An extensive list of different types of irregularities, structural irregularities in a building. Type number 1, which appeared to be a very important one, is vertical stiffness irregularity. And if you remember, we said that for type 1 was one of the critical ones, which totally prohibited using simple method in seismic category 3 and 4. Let's see what it is. Vertical stiffness irregularity For concrete and masonry shear walls, vertical stiffness irregularity shall be considered to exist where the lateral stiffness of the SFRS is in any story is less than 70% of the adjacent story or less than 80% of the average stiffnesses in the 3 stories above or below. So basically it's about change in stiffness, story stiffness suddenly using a less stiff story because say we cannot use brace suddenly certain floor because of the client requirement. You cannot use braces and braces provide good stiffness, then maybe you are using moment resisting frame in that story, which is very good for the activity. However, you are ending up with more trouble in terms of design because although that the story is ductile, remember ductility and stiffness are two different issues. So the one story which is moment resisting is ductile, but it's not stiff. And now you have vertical stiffness irregularity. And yeah, these numbers here, you should be able to find them and use them. If you have to reduce stiffness, you can make sure it's at least not less than 70% of the neighboring stories. And this vertical stiffness irregularity could completely cause rejection of the simplified solution. Then there is weight, mass irregularity. Again, there is numbers about that, and that's about having a story which is very heavy comparing with neighboring stories. And remember that, like generally we said, increasing mass has the same effect as reducing the stiffness. So these two, 1 and 2 they have slightly, they could be, we can think about them that they have some similarities. The period of that story is changing in certain ways. It's increasing, lengthening because the weight has increased or because the stiffness has decreased. Vertical geometric irregularity is number 3. That's when the dimensions change. The horizontal dimension of seismic force resisting system in any story is increasing by 30%. That's number 3. Number 4, in plane discontinuity in vertical lateral force resisting system, except for brace frames and moment resisting frames, and in plane discontinuity shall be considered to exist where there is an offset of a lateral force resisting element of the SFRS or a reduction in lateral stiffness of the resisting elements in the story below. So the second condition, stiffness, ties with number 1, but number 4 is more about discontinuity in plane. And out of plane offsets, discontinuities in lateral force path, such as out of plane offsets of the vertical element. So when the vertical elements are like they are not behind each other, they are offset from each other. That's considered irregularity as well. Pictures here. Vertical stiffness irregularity, meaning that you are very stiff up to some point, and then you say, okay, now there's less weight above, therefore suddenly reduce. Like in this case, you suddenly, or the designer have suddenly reduced their stiffness, and they have caused this irregularity. Vertical mass or weight. I don't know if the code emphasizes or not, but then for like some of these rules are softer when they're applied to the roof level. So the code is not as much concerned about the roof level. So maybe this is a summary because yeah, this I know that in ASCE it repeatedly says that this doesn't apply to the roof level. So that's something just general engineering judgment. We are not as much concerned with a major change at roof level rather than like in mid levels. Weight irregularity is more about suddenly having a heavy level. Maybe here it's a taller level where more equipment can sit and had caused it to be heavier. Vertical geometric irregularity. So remember that by geometry, we mean the geometry of the seismic force resisting system. So the geometry of seismic force resisting system has suddenly reduced from 3 days to 1 day. Or the geometry of the seismic force resisting system, which appears to be moment frame, changed suddenly from 4 days to 2 days. And yeah, so this one is in plane discontinuity in vertical seismic force resisting system. That's within the plane of seismic force resisting system, but then suddenly the resisting from this panel jumped into this panel. So suddenly, like the load pad, thinking about load pad, the load pad has come down up to here, but it should suddenly transfer to the other side of the building. Or this one was full panel and suddenly they required an opening here and therefore the stiffness changed. And in terms of offset, they said that they may just change out of plane as well. So like the picture I had in mind before coming to this slide was that, say these two are in one elevation and the rest are in the other elevation, so there's an offset. So that's definitely type number 5. But the picture that I have taken from other sources, other books, has shown that like in the lower floor, they were at the far ends, and then yeah, it's almost the same concept. So like you had this wall at the lower floor, braced or shear wall, and then suddenly in the upper floors there is an offset and the other walls like the shear wall location or bracing location switch to another elevation view. So this one they switch between the same plane, this one they switch location out of plane. So either one of them need more care, more analysis, more detailed modeling, better solution rather than the more naive pseudo-static solution that we have provided. 5 more irregularities to go through. Discontinuity in capacity. As I said, like both stiffness and capacity are important. We discussed the issue with stiffness, but this is about capacity, strength. So we cannot have, or we can have, but we need more analysis. That irregularity is when there is a weak story, is one in which the shear strength of that story is less than that of the above story. So, I mean, it's like a reverse order. When you go higher, you have higher capacity that will cause issues. The story shear strength is the total strength of the seismic resisting elements. So that it doesn't give you percentage, but it's more descriptive rather than percentage. That's when you suddenly go from a weaker story to a stronger story. Torsional sensitivity. Torsional sensitivity should be checked. There are equations for that. And it's more about having a building where the center of mass and center of stiffness are not the same. Number 8, again, non-orthogonal systems. Majority of buildings, they have two major directions which are perpendicular to each other and they are braced. However, it's imaginable that you can design a building where these two directions are not perpendicular. I mean, I would encourage to do that, have different types of structures, but that would be at a much larger consulting cost because they need more analysis and more rigorous design. Number nine is gravity-induced lateral demand irregularity. Gravity-induced lateral demand irregularity shall be considered to exist where the ratio calculated exceeds 0.1 for seismic force resisting system with self-centering characteristics, and 0.03 for other systems. So we can, if you want, we can go through that sentence again and explore it further, but we will see it schematically as well. And a sloped column, again, when your column has a slope, again, that's considered an irregularity for earthquake design, and it requires more careful design. So a lot of it is almost common sense, like when you don't have a very cubic regular structure, do more analysis and be more careful with the design. Weakest story, like the upper stories are obviously well shear walled, and then suddenly the first story is not shear walled. So here we are not talking about stiffness, we are talking about the strength. So this picture indicates that the first story has less strength. Torsional issues, that's when, say, I think we had that examples and discussions that say for the direction shown, the center of stiffness is halfway between these two walls, but the center of mass is almost at the center of surface. So we have some eccentricity, and that eccentricity has caused the irregularity. Non-orthogonal system, again, I don't say that it's prohibited, but it's prohibited to use the simple solution for assessing that. And this structure potentially can provide resistance and load path in any direction, because these two directions, like there are two independent directions, and therefore the load that comes in any direction could be divided between these two directions. However, there are some torsional effects, etc., that result in like not being able to use simplified equivalent static solution. That's all we are talking about. We don't say that this is impossible. We say we need more rigorous analysis. So talking about the accidental torsion, which is one of the important issues in the code. Accidental torsional effects applied concurrently with Fx shall be considered by applying torsional moments about the vertical axis at each level for each one of the following cases considered separately. So 10% of the dimension in that direction, and the force, the force in certain direction, and the size in the perpendicular direction in a way. This is because maybe we were not exact in estimating the center of mass, and therefore there is some torsion, and we need to design our structure for that in a way, for that torsion. And positive and negative only means that consider both directions. So we have this scenario. This structure has center of mass almost like our best estimate in our calculations has been center of area of this rectangle. And however, we consider that maybe we were wrong by 10%. So we switch it to right and left, and we apply the load 10% to the right and left, 10% of this dimension. So that's what the code is requiring us to do. And it will cause the like unequivalent, basically deflection at the two ends. I think in ASCE there is extra measures where you compare these two and make decision whether like the maximum deflection and the minimum deflection. They give you a measure to compare these two and make decision if additional eccentricity is important. But the way I understand, the MPCC says always check additional eccentricity, always use accidental eccentricity or torsion. But ASCE gives a measure comparing these two values and make a decision whether you need additional eccentricity or not. But if it's me, if I'm the engineer, I always do that because I mean, we are not exact in locating the center of the mass. It's like a sensitivity check in a way that we always do for any design, like to see if our design is sensitive in slide. Sorry, I'm going back and forth too much. I mean, that we always do sensitivity to certain issues, and like in this case, we should see if our design is sensitive to location of center of mass. If the design changes by a lot, if we have wrongly estimated the location of center of mass, and the code gives us a guideline, just change the center of mass location by 10% of this dimension and check your structure, do an additional check on your structure. That's pretty much what the code is telling us. Period values. Yeah, so we all know general concept about the period and how we can read periods from a modal analysis. However, the code also gives us a simplified solution based on the height of the structure. Different equations for different types of structure based on experience that they have. So basically, TS is the fundamental lateral period of vibration of the buildings. For steel moment frames, this solution for concrete moment frames, for other moment frame, that all of them are based on height, but this one is based on number of stories. However, like a person like me that cannot really memorize these ones, I can at least memorize the middle one. Middle one for me is like for a quick back of envelope calculation. I always use the middle one. I divide number of stories by 10, at least for a very quick estimate. But if you want a better estimate, you can open your PDF of MPCC, which is available and it's free. So there's no excuse not to use it and get a much better estimate for different types of the building. Then similarly for brace frames, like you see that brace frame is using has a higher multiplier, which means that generally it's like a stiffer brace frames. We expect them to be a stiffer. Shear walls are also then stiffer than the brace frame. So that's what the code provides us. But yeah, any structural engineer, I would say, should at least memorize this one. like for a building, for your typical building, the number of stories divided by 10, that's a very quick, although slightly imperfect, but quick estimate of the period of your structure. For building a structure, that's what I mean. Now the story drift, lateral deflections obtained from a linear elastic analysis and incorporating the effect of torsion, including accidental torsion, should be multiplied by this factor. So remember that when we were discussing the ductility issues, we always said that most of the time we assume that the deflection without the effect of ductility was already correct, but the forces were overestimated. So the reduction factors, these two reduction factors, or as the code calls them, modification factors, they are intended for force estimate, not for deflection estimate. But when you are going through your steps, you create a model and then you apply the forces which are reduced to that model. And then you read forces which are useful, but then you also read deflection, which are now underestimated. And therefore you should, in a way, reverse that order and multiply your deflections by those reduction factors. So when you are going through the whole procedure and create a model and radial deflection, those deflections are underestimated. So reverse it and then increase them by modification factors. However, in terms of importance factor, again, we said that importance factor we apply because we want to really slightly over-design, push for over-design of important structures. But then again, it causes wrong deflection estimate. So we divide it by importance factor. So that's basically the philosophy that for these parameters, reduction factors, modification factors, and for importance factor, we reverse it when we are reading the deflections. For buildings with a type 9 irregularity, and where importance factor I sub E, I should change it to I sub E multiplied by S is equal or greater than 0.5, deflections should be increased by 20%. So let's go back, remind us what type 9 was. So gravity, that's where the gravity, like you have eccentricities, where gravity is also causes additional deflections. So it says just increase your estimate, what your program gives you as deflection, increases by 20%, because maybe gravity is causing P delta effect, which like you will have some lateral force coming from earthquake, pushing your structure to the side, but the gravity is placed so that it causes extra P delta effect and you will have more deflection. So the code says in order to be safe, increase it by 20%. Effect of foundation rotation and increasing drift should be considered. So yeah, maybe the foundation lifts off, like in your SAP 2000 model, you tie the location of foundation, but in reality, maybe your foundation will also lift off during the earthquake. Account for that in a way, or other estimate or modeling, or else account for that, because that will also contribute to the deflection. So the limits of a story drift for very important buildings, we have the highest limitation, 10% of the, 1% of the height. For buildings of high importance, 20% of the height, and for buildings of normal importance, 2.5% of the height. So 1%, 2%, and 2.5%. However, the golden number that the structural engineers always remember is 1%. So generally, we think about not having a deflection greater than 1% of the height, but practically we know that the code allows for more. So I mean, that's generally, maybe at least for my generation of structural and quick engineer, the built-in number, the first number that we think about is 1%. But sometimes, in some cases, even could be more stringent, and appears that per code for regular structures of regular importance, even up to 2.5% is allowed. That's also an important issue to be designed for. That's in terms of operability and serviceability of a structure and comfort feeling in a way. NDCC structural separations. Sometimes we need to be more stringent because there is if two buildings are built so closely, two high rises are very close to each other, we need even more stringent limit because we don't want those structures to hit each other. And we use the square root idea. I mean, the idea behind a square root is that, if we think that two buildings are moving towards each other, they may hit each other, but it's less probable during earthquake. Maybe they move in the same direction, or maybe they are moving random directions. So we can relax it slightly and apply the separation in terms of a square root, like a square root. Instead of sum of the movements, we use a square root of the sum of the squares, which results in a smaller value. So we, the code had made it slightly less stringent because there's no coordination, especially there's no reverse coordination. We cannot imagine a scenario where earthquake is happening, one building is moving in this direction and the neighboring building is exactly moving in the opposite direction and they hit each other. Therefore, the code had made it slightly easier. And that was with the engineering judgment. But if the buildings are connected to each other, that's a different story. That's you design that connection. That's a completely different story. But if they are assumed to be separate from each other, then the code tries to prohibit they hit each other. If they are connected, then you design the connection one way or other. One way or other, either that connection can carry the whole load so that they move together, or maybe it's innovative and it can slide a little bit so that they can get close to each other, but then that's connection design rather than two separate buildings. Load combinations, such as everywhere else in structural engineering. Structural engineering is all about load combinations, especially in ultimate limit state, where we call it sometimes LRFD, where we apply factors to the load and also to resistance. And maybe this one is what you are familiar with, only dead load, and then where live load is involved, and say snow is involved. Those should be in other courses. When wind is involved. Number 5 is the only one where we have earthquake. So when earthquake involved, that's the additional one because of this course. Live load factor increases to 1 for storage, equipment areas, and service rooms. So we account for some of the more permanent live loads during earthquake. The companion loads must be omitted when they contract the effect of the seismic load. The way I understand it is that, like, if snow load, like we are using half of the live load as companion load, or 25% of the snow load as the companion load. But if, because of the way the load is carried down, the load path of earthquake, snow is really helping with the stability against earthquake, then you don't use snow. Or similarly, if live load is helping with providing stability against earthquake, then don't use it, because like we don't want them to be helping with the stability or a strength. We want them to increase the demand, not reduce the demand. So that's your typical scenarios of load combinations, or some of them, some in the important ones. And number 5 appears to be, that's the only one which is earthquake related. So related to our course. And again, good engineering judgment is that don't use companion loads if they are helping. Only use them when they are increasing the demand. Moving on, modern design philosophy. So again, jumping back to higher level thinking, we use the standard design spectrum. We try to see how NBCC 2020 tell us to create the design spectrum. Like in the US, or in a lot of codes in the world, the design spectrum looks more like a flat line and then a curved one. NBCC more looks like a multi-line, the way I understand it. Like it gives you at certain points and then you can connect them. But all of them are almost mimicking the same idea. So in the mind of earthquake engineer or classic earthquake engineer, the design spectrum always looks something like this. And maybe another line here, which we don't use the other line in building design. But in the modern NBCC, it's more like multi-line, the way I see it. But that's generally the idea of the standard design spectrum concept that has been used in codes and has been taught in the schools for like maybe half a century. Given T, a spectral acceleration is found directly. Spectral displacement and velocity can be determined. So you create this based on the code, and then you can just read the value of spectral acceleration, which multiplied by mass is practically your first estimate of the forces. And then we talked about a few other factors that come in. So there are some constants related to soil conditions. We talked about the effect of the soil condition, and that in the new website of NBCC related to NBCC, those soil effects are already built in, which I like it because we don't need to think about it or make mistakes about it. But classically, we think part of this is flat. There is an upper limit to the spectral acceleration, and there is a curved portion which has a reverse relation with period. That's a general classic picture of a spectral acceleration plot. And the US one still looks the same, and it provides you up to the latest one that I have seen, which is probably 2022. Still the same idea, provide you a guideline on how to estimate this point. And on the left side of it is pretty much flat. And on the right side, it's like a reverse relation with period. And they also provide an additional curve for very long periods where the reverse relation is with period to the power of 2. Then again, modern design philosophy, the effect of the reduction factors, the design spectra versus demand spectra. So the elastic demand, if we think that everything is really remaining fully elastic throughout the earthquake, is a higher value. That's the original SA. But for design, elastic design spectrum, that's a little bit confusing because we are using the word elastic again. What we mean is that do your modeling elastically, but this curve will take care of the inelastic effect. So by that particular textbook repeated the word elastic again, which means that to be used in companion with elastic analysis. So in your analysis, you don't need to account for nonlinearities. You do completely elastic. This curve will take care of nonlinearities and ductilities. And that's why it is reduced by a reduction factor. That's again another high-level concept that is repeated in different books, that there is a reduction factor. In Canada, there is like a reduction factor because of ductility and reduction factor because of overstrength, where we go from elastic demand to the design spectrum. Let's not even use this word because I will be confused by repeating the word elastic. So this is the design spectrum, and the top one is elastic demand spectrum. Unique features of seismic demand. The seismic demand is cyclic, so increases and reduces like in 1 minute. And there are some short duration bursts in a very small time. It reaches its highest shock, and it's not harmonic, so it's not like exactly sinusoidal, although it's cyclic, like increases and reduces, but it's not exactly harmonic. That's the general characteristics. That was the idea that resulted in the philosophy of earthquake design. So the ratio of elastic response spectrum to the design spectrum is typically between 4 to 8. So a spectrum for elastic design, the elastic demand spectrum, and the ratio of these two is the reduction factor that we have been using. And this here we have tried to, like in a picture, schematically show why the elastic demand is this high. We use a capacity which is this low. The reason is that on one hand, the structure becomes nonlinear, and when the structure becomes nonlinear, the demand reduces. On the other hand, the capacity of the structure because of over-design, over-strength is higher, would be higher than what we will prescribe. So the two factors that are separated out in Canadian code, we can see both of them here. On one hand, the ductility reduces the demand. On the other hand, the over-strength increases the capacity, and really these two meet each other at this point. So the structure remains adequate because the capacity is more than what we designed for, and the demand is less than what we think it is in an elastic curve. that ratio, that reduction factor, a lot of time is between 4 to 8. And in Canadian code, you can look at those numbers in National Building Code of Canada. And like when you multiply the overstrength reduction factor by ductility reduction factor, you see a lot of them really are between 4 to 8. The modification is a combination of the reduced demand due to ductility, in Canada we call it RD, and increased capacity due to overstrength, that in Canada we call it RO. So high level earthquake engineering philosophy, that's what we have. Some more about the high-level modern design philosophy. Performance benefits of inelastic deformation, or also known as ductility. Because we provide ductility, we dissipate energy. That's when the structure really yields. The poster boy of materials, good material is a steel. So you can always start thinking about the steel, but then try to extend it to reinforced concrete, etc. It still yields, and it goes through these circles and dissipates energy. You get rid of that energy shock caused by earthquake. And the ductile members are protecting non-ductile members, but provided that we have designed connections well and we have used the capacity protection philosophy. The load is redistributes, like if one part of the structure at the end of the day is stiffer than the other part, and it's taking the whole load, when it yields and softens up, the load distribution improves, like the other members also become active. So that yielding helps with redistribution of load. And we should be aware that the dynamic characteristics may change. Softening normally means a longer period. So we switch to longer period. And ductile structure dissipates energy, doesn't allow the force to go higher than certain limit, and changes the period. While if we had remained elastic, so the dark borderline is the real ductile structure that we have. And however, if the structure had remained elastic, energy dissipation was minimal, the forces would have been larger as well. So disadvantage right there. The inelastic deformation alters dynamic characteristics, and period shift could be beneficial. That's part of the knowledge of the structural engineer, that if the initial estimate of period was T0, and because the structure has softened, the period increased slightly or even more, the response decreases. And then we can go to any typical design spectrum. If our estimate of period increases, the demand reduces, or here as well. So that should be also built into your earthquake engineer judgment. And again, going back to capacity protection, the idea behind capacity protection was to have a weak link in the load path, and the weak link must be ductile. So that's the concept shown in chain, which is a load path from top of the structure to the earth, and the load goes through a bunch of members in a way, and there's a weak link where we wanted it to be ductile. In real life, so the load path starts from top frame where the inertial, most of the weight is, and therefore the inertial load really starts there and goes through the diaphragm and connection of diaphragm to the frame and comes down to the steel frame, say here, and or steel bracing, where we want ductility to happen and we want the weakling to be the frame. So that's the concept behind capacity protection. Like any other member should be stronger than frame so that the damage happen in the frame, if any, or the failure happen in the frame because we designed the frame for that purpose. We don't want damage in diaphragm above, and also we don't want damage in connection to foundation or foundation itself. We want everything to happen in those braces. We are getting to the end of the class. We are in good location. Next time I can re-emphasize the philosophy and then jump onto the faster path to the end. But I'm hoping that you guys are enjoying this very important modules of the course about the design philosophy and about the NDCC. And I hope everybody is having a great weekend. Hopefully I didn't miss any other questions. Please submit your draft reports tonight and then continue your work. And we will give you feedback by about the end of next week, sooner or later, so that you apply our progress, at the same time apply our comments by myself and then and then you will have your final submit already 2 weeks from now. And yeah, after you submit, go and enjoy the long weekend and reading break. I will be talking to you next Friday. Have a good weekend and bye, everyone. I'm sitting here 1 or 2 more minutes if there is a question or discussion. Take care.
Hello, Ali. Can you hear me?
Microphone again, yeah.
Okay, I just had a question regarding the draft report. Is there like a specific rubric or guideline like to show us like what needs to be there in the draft report? Because we were working on the dam earthquake engineering, and we have referenced like the Canadian Dam Association guidelines and all that, but like, do we just need to like just talk about the earthquake in the guidelines, or is there like more details that we need to add?
Yeah, last year, yeah. Thank you for bringing this up. Last year we created a rubric, but mostly focused on the final submittal. We wanted to like treat different projects equally. So we created a rubric for the final design.
Yeah.
So this year we don't have a final rubric yet, but generally we will try to do equally to all teams.
Yeah.
There's no emphasis on math or modeling or so some people prefer models, some prefer research. All are good as long as you have something to say. Think about it as say you will be presenting it. Do you have something to say in 20 minutes to teach us? That's absolutely fantastic.
Okay, and like for the report,
things like that, yeah. Sure. Yeah.
For the report, how long do you think the report has to be like
Yeah.
because
Well, that's
I
a
don't
good
know how.
question. Yeah. Another team also asked me. I went through the previous year. They were order of 40 pages, main body. Some teams had a lot of appendices, some didn't. So yeah. So for final, so maybe I don't know if you are at 70%, then that would be how much? 30 pages now, and then you add another 10 page in the next 2 weeks. But if you are thinking only in terms of pages, a lot of people say concept is important, but concepts goes into pages. So think about that.
So if we don't have like we kind of have like 10 pages in, so we don't have all that content yet. So is it okay if we submit whatever we have for the draft, or is the draft marked on the basis that we finish the entire report, or is it like what you have so far?
We want you to have touched everything, so you still have maybe 10 hours. Try to do more, so you try to really touching all the concepts, but maybe it's not exactly where you want it, but then just touch them. So it looks like 10 should be on the smaller size, but your team, if you can get together, 10 hours is a lot of time, so maybe you can. Oh, sorry, that would be late at night. But then, try to do more before submitting. That's what I suggest, and you will be happy because then you will enjoy your weekend.
Oh yeah, sure. Okay. Yeah. Thank you.
Yeah.
This was helpful.
Thank you. Yeah. All right. More questions?
No, I think that's all for now.
Okay. Thanks, Chingish. Yeah.
Thank you. Bye.
All right. Take care. Bye.